Hi class, it's me, Mr. Morris, and this is a video on the gas laws. Okay, we're going to start out with kinetic molecular theory, and we're going to go all the way through a review of all of the gas laws. So there's a lot to this. There's a lot to this set of notes, but I'm going to try to move as quickly as I can. You might have to pause the videos to catch up a few times because I'm not going to be crunching numbers in the calculator like I do sometimes. All right, to start out with, we want to talk about the variables that affect gas. We've got pressure, which is the force that the gas exerts on the walls of the container. So in other words, gas particles exert pressure when they collide with the container walls. Okay, so that container can be anything. It could be a cylinder, it could be a balloon, it could be a lot of different things. But when they collide with the container walls, pressure is built up. Our units of pressure are atmospheres, kilopascals, millimeters of mercury, and torr. Now, I want you to know that millimeters of mercury and torr are identical. That's why 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 760 torr. 101.3 kilopascals is the conversion to 1 atmosphere. All right, the temperature. Temperature is another variable that affects gases. It's a measure of the average kinetic energy of the gas particles. So, kinetic energy is directly proportional to temperature in Kelvin. So kinetic energy is directly proportional to the temperature in Kelvin. When we're working with gases, the temperature is always measured in kelvins. The way to convert to Kelvin is by adding 273 to your degrees Celsius. Temperature in Kelvin is absolute temperature. We call that absolute. So that means that there are no negative temperatures. They're always going to be positive. Okay. Another thing, we do not write, let's just put this here. Don't write degrees Kelvin. It's just kelvins. So if I have 273 Kelvin, I'm going to just write 273 K. Don't write a degree sign for Kelvin. All right, volume is the space that's occupied by gas particles. It's just like volume for a liquid, the same units, but we usually measure it with a different type of device. The space occupied by the gas particles, so our units are liters, milliliters, and centimeters cubed. Don't forget that a centimeter cubed and a milliliter are the same thing. So if I have 1,000 centimeters cubed, that's also 1 liter. Okay, the amount of gas, or in, we measure that in moles. We've got to convert to moles if we want to use our gas laws. To convert to moles, of course, we're going to use our molar mass, because 1 mole equals the molar mass in grams. We use the periodic table to find the molar mass if you didn't remember that. Okay. Standard temperature and pressure, or just STP, are kind of these arbitrary numbers that we came up with that is a standard for the amount of pressure and temperature that you have. So standard temperature is 273 Kelvin, which is the same as 0 degrees Celsius, so it's the freezing point of water. Standard pressure is 1 atmosphere, which is 760 millimeters of mercury, also 760 torr because those are equivalent, and 101.3 kPa, kilopascals. Let's go to the next page. Now we talk about the actual gas laws. The first couple that we talked about last year were Boyle's Law and Charles' Law. That's where we're going to start here too. Before we even get started, I want to practice just looking at a graph and identifying what kind of relationship it is. If it's a straight line increasing like that, that means as this number increases, and it's a linear relationship. We say that is a direct relationship. This is an inverse relationship because as this number increases, this number decreases. See, as we go across, that's going down, but it's not a straight line. That's because this is a fraction and we get something called an asymptote. You've probably heard that in math. Okay, so an inverse relationship has that curve. So this is inverse, that's direct. If you could look at these other graphs down here, you could identify they're also direct. And this one is also direct. And we'll go through each of these, starting with Boyle's law. In Boyle's law, the variables that are changing are volume and pressure. So volume and pressure, and the variables that stay constant are the number of moles and the temperature. Our formula is P1 V1 equals P2 V2, and it's our only relationship that is inverse. One way to remember that is we say that Boyle is the VIP. Volume is inversely proportional to pressure. If you can remember Boyle is the VIP, that'll help a little bit maybe. Okay, Charles's law. Temperature and volume are directly related. So temperature and pressure are being changed. I'm sorry, not temperature and pressure. Temperature and volume are being changed. So temperature and volume are changing. The variables that stay constant are moles and pressure. Formula we use for that is V1 over T1 equals V2 over T2, and the relationship between the variables that are changing, volume and temperature, are directly related. It's a direct relationship. All right, let's look at the next law, Gay-Lussac's law. Oh, and if you were wanting to remember how to remember this law, you say this is temperature and volume, so that's TV. You could maybe remember something like good luck, Charlie. Because Charles's law is on TV. Good luck, Charlie on TV. Or any other TV show that has Charles or Charlie in it. All right. Gay-Lussac's law. This is the one that we say the guy lives in a teepee. The guy that lives in a teepee. Okay? Variables that are changing. Well, down here, and you can't actually read this on here, but it's temperature and pressure that are changing. That means our moles and our volume are the constants. P1 over T1 equals P2 over T2. That's our formula. And the relationship between the changing variables is a direct relationship. Remember, the only inverse relationship is Boyle, because he's the VIP. All right, Avogadro's law. Avogadro sounds like avocado. Avocados are green with envy in V. I know it's a pun, but it works. Okay, because the moles and the volume are what's changing. Our relationship is V1 over N1 equals V2 over N2. I almost forgot to write what's constant. The constants are temperature and pressure. The relationship between the changing variables is direct. It's a direct relationship. Okay, so we've got these 4 laws, primary laws. These 3, we can combine them together in something that we call the combined gas law, and I think that's where we're going next. Yes, it is. All right. The combined gas law, the variables that are changing are pressure, volume, and temperature. Variable that stays constant, usually we leave moles alone when we're doing a combined gas law problem. There is a version of it that includes moles, but usually moles don't change. Formula used to connect them is going to be P1 V1 over T1 equals P2 V2 over T2. The relationship, well, P and V are inverse. P and T are direct. V and T are direct. And we could mention N and V, but we won't right here. Okay. Go on to the ideal gas law. Just the general concept of the ideal gas law comes from combining all of these together and coming up with a relationship. All right. So if I were to put these together, this is, by the way, let's run through that again just to review Boyle's law. Okay, TV, that's Charles. TP, that's Gay-Lussac. Okay, NV, that's Avogadro. All right, and then P1 V1 over T1, P2 V2 over T2, this is combined. But if we take all of those concepts and just kind of hybridize them, what you'd come up with is this. You come up with this ideal gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. That fraction is equal to R. R, we could say R equals PV over NT. And at any temperature, pressure, number of moles, and volume, if you did that, you would find something at least very close to R. You could derive R in an experiment that way. There's a few different values of R. We want to write them down the way that it's going to appear to you on the AP exam. So one value of R is 8.314. And the units of that one are joules per mole degree Kelvin, or mole Kelvin, sorry. Joules per mole Kelvin. Joules times inverse moles and inverse kelvins. That means joules divided by moles and also divided by Kelvin. Kind of a unique way of writing units. Okay, this is the one you're probably more familiar with and you've used it more often, or at least something very close to it. 0.08206 liters times atmospheres inverse moles inverse kelvins. So liters times atmospheres divided by moles divided by kelvins. So you've probably seen it written that way. This is probably the way we wrote it last year. Liter atmospheres per mole Kelvin. It means the same thing. So when you see these units, just know that they're the same as those units up there. All right. But you're going to see those constants on a test. It's the way that it's written. The relationship between the variables in the equation is described down here. We want to run through it. Pressure and volume, how are they related? They're related inversely. Okay, pressure and volume, they're related inversely. They're being multiplied by each other here. So if one goes up, the other one has to go down. Pressure and moles. Well, if one goes up, the other one also has to go up. So that's a direct relationship. Pressure and temperature. If that goes up, the other side also has to go up. So that would be a direct relationship. Volume and temperature. Well, if volume goes up, temperature on the other side also has to go up. So that's a direct relationship. And then volume and moles. Volume goes up, moles would have to also go up. So that is a direct relationship. All right. The ideal gas law can be rearranged and combined with the formula of density and the definition of molar mass to come up with this equation. Molar mass equals dirt over P. I would memorize this. Molar mass equals dirt over P. You only use this if you're dealing with problems that involve molar mass and or density of a gas. I want to derive this with you real quick though. And don't worry about it too much. You don't have to be able to do this on your own from scratch, but it's just kind of a good exercise to go through. So please stick with me. We're going to do this in steps. The first step is by plugging it into PV equals nRT. So I've got PV equals nRT. And we're going to use some definitions to plug into here. Well, one of these things that I can plug in, I immediately see that N is a part of this. So I could use the definition of molar mass, and I'm going to substitute something in for in this equation. So let's write down our formula. Molar mass, I'm going to represent it with capital M, capital M. Molar mass is equal to mass over moles. So we're going to say M over N, mass over moles. Now, I want to plug in the letter N into this formula. So I want to find out what is N equal to if I rearranged this equation. Well, we could see that N times molar mass equals mass, and N equals mass divided by molar mass. All right, so that's what N looks like. I could take that number and I could plug it in right here. Then move on to my second step, where instead of putting in there, I'm going to put M over MM. So I end up with PV equals M times R times T divided by the molar mass. We've got M over molar mass times RT instead of the N there. If you need a second to pause and justify that, that's fine. Okay. Now I want to look at density. I need to look at my density formula up here and see if there's a way that I can plug that into this. All right. Well, density is mass divided by volume. So I see mass in my formula and I see volume in my formula, but they're not on the same side. So I need to change that. I could divide by volume on the other side now, couldn't I? So let's do that. Because density, and I'm going to just write this here as a reminder, density equals mass over volume. I'm going to use that in just a second. Okay, so I end up with pressure equals mRT over V times molar mass. Do you see that I've got density right here? Got density right there. So I took that and I plugged it in to my equation. I could rewrite this. Because of this, I could say that pressure equals mass over volume is density. Density times RT divided by molar mass. Or I could say pressure times molar mass equals dRT. Or finally, I could say molar mass equals dRT divided by pressure. So that's how that formula is actually derived. This formula right here. It's the same thing that we have up here. Okay, that's how it's derived. I wanted to spend just a couple minutes on that. If you don't want to have to do all of this to justify it, maybe you can just put that to memory. Okay, this one I don't think will be given to you, but it's useful if you're ever dealing with a density problem with gases or a problem that involves molar mass with gases. You want to know the formula: molar mass equals dirt over P. Kind of a silly way to remember it is just try to be a good kitty. Okay, a good kitty, your kitty litter box. If you're a good kitty, you always put dirt over your pee, right? I know that's disgusting, but it works. And Dalton's law of partial pressure. We talked about this a little bit last year. This is used when we have a mixture of gases. You do not use this for just one gas. It's a mixture of gases. A partial pressure is the pressure a gas would have or would exert if it were alone in the container. If it were the only gas in the container, how much pressure would it have? That's what a partial pressure is. Dalton's law of partial pressure says that the total pressure in a gas mixture is the sum of the partial pressures of each individual gas. It sounds kind of like common sense, and it kind of is, but some of the problems can get a little bit complicated. Okay, so what we're saying is your total pressure is the sum of each individual gas. We have PA, PB, PC, but we could think of it as like pressure of oxygen, pressure of nitrogen, pressure of helium, whatever the mixture of gases contained. Dalton's law of partial pressures assumes each gas in the mixture is behaving like an ideal gas. We'll talk about deviations from ideal gas behavior later in the year, but right now we're assuming that these are ideal gases. That means they do not interact in some chemical fashion like reacting, like a chemical reaction. Okay? Pressure 1 and pressure 2. So I've got these two different gases. We've got the same volume. If I have the same gases, same pressure, or if I have this pressure of this gas and I've got this pressure of this gas, and I put them together in the same size container, it's just the total pressure equals the pressure of this gas plus the pressure of that gas, as long as the container size is the same. It gets tricky when your container size changes, and we're going to talk about that in a minute. All right, our mole fraction. The mole fraction from the partial pressure of a certain gas and the total pressure of a certain mixture, the mole fraction called Xi of a gas can be found. All right, now this capital X, and then we have a subscript of something. In this case, it's Xi. It could be X of whatever the gas is. That's really what it means. Okay. So the mole fraction describes what fraction the mixture is. What fraction of the mixture is a specific gas. So talking about a specific gas, what fraction of the mixture is that gas? For example, if oxygen exerts 4 atmospheres of pressure in a mixture. So we've got oxygen, 4 atmospheres of pressure in a mixture, and the total pressure of the system is 10 atmospheres. Then the mole ratio would be 4 over 10, which would come to be 4. The mole fraction applies to the pressure and the moles, as seen in this equation down here. So the number of moles of a particular gas divided by the total number of moles in the mixture of all of the gases is equal to the mole fraction, and the pressure of that particular gas divided by the total pressure of the mixture will give you the same number. So in our example over here, what we're saying is the number of moles of O2 over the number of moles total, like the mixture, whatever else is in the mixture, is equal to X of O2. This is just an example. X of O2 equals N of O2 over N total. It also is equal to the pressure of O2 over the total pressure. That's the concept of the mole fraction. It's often used to determine the composition of gases in a mixture. All right, the sum of the mole fractions of each gas, so the sum, if we added up the fractions of each gas in the mixture, they should always equal 1 since they represent a proportion of each gas in the mixture. So if we add them up, it's just like adding your percents should always add up to 100%. Since this is a fraction of 1, each of those mole fractions added together should add up to be 1. On the AP test, you're going to see this form of the formula. You will also have this form of the formula. You will have both of those given to you on the formula sheet on the AP exam.